Time to bring chapter 16 to a close and take a look at the last topic that we have for at home chapter 16 in equilibrium and acid bases, and that's the base strength ionization constant or equilibrium law called Kb. So this is going to apply to our weak bases because we are looking for the equilibrium system. So remember, strong bases are things that react completely just like strong acids were. So what we're looking for is our ionic hydroxides. So things like sodium hydroxide, lithium hydroxide, those are highly soluble, and so they will dissociate completely in water, producing a maximum strength of OH ion concentration. We also have some soluble metal oxides. We haven't really seen that too much, but there's a good example on page 744 for you to check out just in regards to that one. Where we're taking a look at it is the weak bases, and so we're looking at molecular compounds here that will ionize incompletely with water, or we'll see certain soluble ionic compounds that will produce anions that will allow us to produce a small amount of hydroxide ion in solution. So those are the ones that we're looking at because they will form the equilibrium systems that we're studying with our ice tables and equilibrium law expression. So examples of weak bases that we'll see quite a bit of here would be something like ammonia. All right, the component of Windex that gives us our nice streak-free shines on our windows, or ammonia solutions, which are weak base solutions. And then we can see some things like a sodium fluoride here, or maybe a sodium nitrite, which are soluble ionic compounds, but don't produce hydroxide directly, but produce an anion that would mess with water's equilibrium, tipping the scales towards having some amount of hydroxide there. This all ends up playing out very similarly to how we saw all of those Ka calculations. There's going to be two styles in which we look at these again. One in which I give a pH or a pOH. All right. If I have that, I generally have given you enough to complete an ice table, or at least the equilibrium lines of your ice tables, and therefore an equilibrium law calculation can be done, and you can go calculate the Kb that you're looking for. With ones when we're dealing with pH and pOH in our basic systems, what you'll find as a slight difference between Ka and Kb is there's usually a little bit more jumping around and bouncing around all of those pH, pOH, hydroxide, and hydronium calculations to get where you want to go. So it just becomes a little bit more intensive in its conversions. Lots of good examples on page 745 and 746. Please take a look at those when you're going through your textbook readings. And I'm going to do a couple for you guys here in the video to take a look at calculating Kb when you've been given a pH or a pOH. So we need to find our equilibrium system first. So as we do this one, we take a look at our entities. All right, and in this one we had, for question number 1, the pH of a 0.1 molar sodium nitrite solution is 7.63, or slightly basic, and I want to calculate the Kb, or the equilibrium law expression, for this weak base. So we just have to figure out what it is. So sodium nitrate is a soluble ionic compound, which means it doesn't exist in water. It exists as sodium ions and nitrite ions when we finally dissolve that particular salt. Don't forget that you've dissolved it in water. And so for entities list, we have a few potential players here. What you need to do now is go through your lists of acids and bases and find all of the potential acids and all of the potential bases that exist in this list of entities. And what we'll find is, well, of course, water is both a potential acid and a base. The only ion that we see that ends up on that list is the nitrite ion. And you will find it down near the bottom, or sorry, near the top of the weaker bases or weaker conjugate bases. So we end up having two bases, one acid. That means water is my strongest acid here. That is my proton donor. And you will find that nitrite is your strongest base. So there's your proton transfer. We have an equation that looks like this. Water will react with the nitrite ion in solution. Equilibrium will be found. We said water was the strongest acid, so it will give up its proton leaving behind in its wake. There's your hydroxide. That's how we got it. And HNO2 as our other entity. Go back to the question. We're told a couple of things, so we can complete our ice table here. Water, of course, doesn't play because it's a liquid. It doesn't have a variable concentration like the others. And we were told that it was a 0.10 sodium nitrite solution. Therefore, the amount of nitrite I get should be that same concentration. I would assume to start from 0. And then the last thing that we're told here is that we have a pH of 7.63. Where do you think pH could be utilized to help start filling out one of those equilibrium lines? Remember, from calculating Kb, I should be able to get to an equilibrium line on my ice table and have equilibrium concentrations to put into my solution. Well, pH doesn't tell us directly, but pH equal to 7.63 should be able to resolve for me an eventual hydroxide ion concentration. Okay? With that one, there's a couple of different ways that we can certainly go through it. We can go figure out hydronium. If you like, we can go figure out POH and go from there. There's lots of different ways that we can bounce through this particular expression. There's no right or wrong way. It's just how you see the conversion to get there from a pH or a POH number. So in this case then, since pH plus POH are always equal to 14, then my POH just has to be equal to 14 minus the pH, which is 14 minus 7.63, which gives me 6.37. So now I have my POH. That's only one step closer to what I need to start working through equilibrium here. I need to get to a hydroxide ion concentration. Well, hydroxide ion concentration is just 10 raised to the negative POH. Okay, well, we just figured that one out. 10 raised to the negative 6.37. If we work that one out, works out to 4.2657, etc., 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 times 10 to the negative 7 moles per liter of hydroxide ion in solution. So because this sodium nitrate solution has a pH of 7.63, it contains this concentration of hydroxide ions. We now have one piece of information that we can use. And we can see it to be a very small amount of hydroxide in solution. If I started at 0, that's my increase. And because of that 1-to-1 ratio that we see throughout, remember, be in the habit of communicating that, and we can see the changes. This should increase by the same amount, giving us that same concentration in solution. And we should decrease by that amount here. And you might notice that what we are doing is decreasing by an incredibly small amount compared to 0.10 moles per liter. So you can run it through your calculator to get a whole bunch of repeating nines, or you can realize that this is a million times smaller than the original concentration. That is greatly superior to that rule of 1,000, and it's really just 0.10. You have an insignificant loss of your original concentration, and therefore we can ignore X. Again, whether you do this assumption or not in these first types doesn't really matter. What you're going to find is that if you write down all of the digits for your difference versus ignoring X in a case like this, you get the same answer once you start running it through your calculator. So, here we go. We can now go solve for the Kb of this solution. We have the hydroxide ion concentration, the nitrous acid, and we also have the nitrite ion in solution here. We can then go put in our numbers, which of course we have as 4.265 and a whole bunch of extras, times 10 to the negative 7. Do that 2 times since it's squared. And we can also divide this by the 0.10 that we assumed as our equilibrium concentration for nitrite after the dissociation. Run that through, punch in those numbers, and you get 1.819 times 10 to the negative 12. All right, a very small Kb value here. We have to fix our sig digs. We had 2 with this, we had 2 with a pH of 7.63, so the 1.8 remains, the 1 rounds down, and Kb in this case is 1.8 times 10 to the negative 12. Okay, very similar calculation. You're just flipping these and looking at it from the point of view of the basic side of the problem now, where pH tells us about hydronium, so we do a few conversions to get to the hydroxide that we need. Okay, so these ones feel very similar to what we've been doing with Ka. They just have an extra conversion here or there. One more example coming for you guys, or sorry, the other 2 examples coming for you guys in the next video, and then we'll move on to ones where we have to look at a strategy to avoid the quadratic.